Hello and welcome again to FlippedHarber for Algebra 2. In this video we're going to cover section 1.9, Introduction to Parent Functions. Our objectives for this lesson are to identify parent functions from graphs and equations. And then we want to use these parent functions to model real-world data and make estimates. Now our topics for this lesson only include parent functions. But as we go through this video, we're going to be looking at 5 types of parent functions. Now there's a lot more different types of parent functions out there. We're limiting ourselves to only 5 of them right now. We're going to look at transformations to these parent functions as well. We're going to go over some examples where we have to identify parent functions and then even graphing and identifying parent functions. So, our first type of parent function is what we refer to as the constant function, f of x equals c. This makes a nice straight horizontal line graph. The domain for this, that is where the x values are for this graph, is any real number. The range, that is the y value, is limited to that constant value c though. And the y-intercept for this graph is the point 0, c. Again, that constant value. We have 3 examples of a constant function on the screen. F of x equals 4. Whenever f of x or g of x or whatever just equals a plain old number, that's a constant function. But g of x, that's also a constant function because, as you are well aware, there are numbers in math that are so important we've given them their own symbol, like pi. So g of x equals pi is a constant function because pi is a constant value. Another example tried to make h of x look kind of weird. H of x equals e squared. E, like pi, is a very specific number in math. It's a constant, and even when you square that constant, it's still a constant. So what you need to really pick up on here is that there's absolutely no independent value in any of these 3 functions. There's no x. If you don't see an x at all, it's a constant function. Our next type of function is a linear function. The parent function is f of x equals x. The graph for that parent function is a straight line that goes through the origin. The domain, that is the x values for this function, are all real numbers, as well as the range, because you can plug in any number and you can get out any number. Our y-intercept for this parent function is the origin, 0, 0. Now let's take a look at some what we refer to as daughter functions. Get it? Parent functions have daughter functions. F of x equals x plus 2. That's a transformed f of x equals x. So we refer to it as a daughter function of the parent function. G of x equals 3 minus x is also a form of a linear function. Its parent function is f of x equals x. H of x equals 3x plus 2 is another daughter of this same parent function. What you need to notice is that x appears once and it has a power of 1. Whenever you don't see a power on a number on a letter, it's what we refer to as an understood 1. So the fact that we see x with nothing fancy on it, no powers or anything like that, it's a linear function, and its parent function is f of x equals x. Our next type of function is a quadratic function. The most basic quadratic function, that is the parent function, is f of x equals x squared. That parent function has this parabola graph shape. The domain is all real numbers. The range is only y is greater than or equal to 0. You can only get out positive numbers from f of x equals x squared. The y-intercept, again, is the origin, 0, 0. Some examples of daughter functions, that is transformed parent functions. F of x equals 4x squared. You stick a number in the front, it's still a quadratic because that x is squared. G of x equals x squared minus 2. Again, the x is squared. Just because we're subtracting 2 doesn't change the fact that it's a quadratic function. H of x equals the quantity x plus 3 squared. You stick a number inside with the x, it's still a quadratic. The important thing here is that there is a square on the variable x. Now, just because there's a squared in the function doesn't make it a quadratic. Think about the one that we saw earlier. F of x equals e squared is not a quadratic function. That squared is not on the x. F of x equals e squared is actually a constant function. We saw that already. Our next type of function is what we refer to as a cubic function. F of x equals x cubed is the parent function. That parent function has this neat step-shaped graph. The domain is all real numbers. That means that we can plug in whatever number we want. The range, also all real numbers, because we can get out both positive and negative numbers. The y-intercept is the origin, 0, 0. Here's some examples of transformed cubic functions. F of x equals 1/2 x cubed and g of x equals 2x cubed minus 4. These are cubic functions because x has a power of 3. Our last type of function, a square root function, the parent function is f of x equals the square root of x. We see this graph is very one-sided. That's because the domain is only x is greater than or equal to 0. We can't plug negative numbers in. The range is also greater than or equal to 0. We can only get out positive numbers from this parent function. The y-intercept is 0, 0. The thing to look for to identify that this is a square root function is that the x, the variable, is under a square root symbol. So f of x equals the square root of x minus 2. G of x equals 3 times the square root of x plus 1. And h of x equals the square root of 2x. These are all square root functions because the variable is under the square root symbol. Okay, so we've gone over our 5 types of parent functions. Let's see if you can identify the parent function for each of these. G of x equals the quantity x minus 1 cubed. What do you think that is? Well, it's pretty obvious. It's a cubic function. The x is getting cubed, so it's a cubic function. What about g of x equals the quantity x plus 1 squared? If you said quadratic, you're right. That x is getting squared. What about g of x equals negative x? That's a linear function. We don't see a power on x, nothing fancy's happening, so that graph would be a straight line. It's a linear function. What about the next one? Pretty obvious, it's got a square root. Yes, it is a square root function. X plus 3 is all under that square root. What about the next one? G of x equals x squared plus 4. That's a quadratic one again. Now the last one. I see a square root. Is that a square root function? No, it's not. It's a linear function. For it to be a square root function, the x has to be under the square root. That x is not under the square root. This is actually x minus just a fancy looking number. This is a linear function. Alright, let's make some graphs and see if we can identify the parent function from the graphs. So we've got 2 tables of values. We're going to plot these points, we're going to draw lines or curves, and see if we can identify the parent function. So let's start with the one on the right. We plot the points. They seem to be in a nice straight line, and they are. So this is a linear function. Now there's fancier ways to tell that something is a linear function, but this is just great for this lesson. What about the other one? When we plot them, we get this weird shape. Do you recognize it? It's a cubic function. Again, there's a fancier way to tell that something is a cubic function, but plotting the points and drawing the curve is just great for this lesson. Alright, let's do a story problem. The time that it takes for a pendulum to complete a swing depends on the length of the string. Now this actually comes to us from the world of physics, something very near and dear to my heart. What we're going to do in this problem is we're going to start by making a graph of this data. From that graph, we're going to try to identify the parent function. And then also from that graph, we're going to try to figure out how long the pendulum needs to be in order for it to take 4.5 seconds to complete a swing. And then we're going to try to use that graph to estimate the time to complete one swing for a pendulum that is 9 meters long. So let's start with that graph. We plot these points, we draw a curve. Does this look familiar? If you said it's a square root function, you're right. So it's actually a square root function that relates the time to complete a swing and the string length for a pendulum. Now, what about that 4.5 seconds? If we go to 4.5 seconds on our graph and go over to the graph, that means that we would need to have a pendulum that's approximately 5 meters long. If we go the other way, if we know we have a 9 meter long string, we go over to 9 meters on the x-axis, go up to our curve. That 9 meter pendulum should take 6 seconds to complete a swing. So, here's our homework for this section. We're all done. This is actually the last section from the chapter, so it's also time to start reviewing for our test. I hope you enjoyed it. I'll see you in class, and I'll see you in the videos.